Welcome to the lecture series on CFD, Part 2. This is lecture 37 on simulation of flows with heat transfer. This lecture deals with simulation of flows involving heat transfer. Introduction to heat transfer and Nusselt number is followed by a description of a method to calculate heat flux at walls, including the case of a thin coating by a different material applied to the wall. The definition of heat transfer coefficient and the controversy around it is also discussed. Heat conduction in solids, including composite materials, is also covered. Natural convection in fluids and its dependence on fluid properties is the next topic. The need to pay attention to limitations of Boussinesq-approximation is highlighted. Simulation of natural convection with unstable stratification is the next topic, followed by the simulation of forced convection in fluids. Finally, attention is paid to the simulation of conjugate heat transfer. Several examples are used to highlight the important topics. Many flows include heat transfer. Fluid is often used as heat carrier. The transport of heat by fluid flow is called convection. Convection can be forced when flow is driven by external forces, for example pump, fan, etc., or natural when the main driving force is buoyancy due to density variation caused by either temperature or concentration variation. In the case of forced convection, if temperature variations are not high, one can first compute the flow with constant fluid properties and then compute temperature variation for the known flow field. Natural convection requires that the energy equation is solved simultaneously with the Navier-Stokes equations because of two-way coupling. In this case, the flow affects the temperature distribution and vice versa. In case of small temperature variation, one can use the so-called Boussinesq-approximation. Density is assumed to be constant in all terms except for the gravity force, which is modeled as follows. Here, T0 is the mean temperature, ρ0 is density at T0, beta0 is the volumetric expansion coefficient, and gi is the gravity acceleration in xi direction. Otherwise, one must update fluid properties that depend on temperature every time after temperature is updated. Whenever temperature distribution affects the fluid flow, the energy equation must be solved coupled to the Navier-Stokes equations, that is, inside the outer iteration loop if the sequential solution method is used. In the flow chart shown in this figure, scalars stands for temperature or enthalpy and any other scalar variable. For example, turbulent kinetic energy, dissipation rate, chemical species, etc. In solids, heat is transported only by conduction. In fluids, both conduction and convection are present, whereby the convection by flow is usually much stronger than conduction. Nusselt number is the ratio of heat transfer in presence of convection to what it would be by conduction alone. In laminar flows, the Nusselt number is usually smaller than 10. In turbulent flows, Nusselt number can be much higher. Nusselt number depends on Reynolds number and Prandtl number. One can find in literature empirical correlations for many situations, for example, for a laminar flow over a flat plate, as given by this expression. Heat is exchanged at a solid-fluid interface by conduction alone. Even in a turbulent flow, immediately at the wall the flow is laminar with a linear temperature variation. The flow, and turbulence in particular, increase heat transfer by leading to a higher temperature gradient at the wall. Heat flux is equal to the product of heat conductivity lambda and temperature gradient. This applies on both sides of the interface between two different materials. Let's have a look at the situation shown in this figure. The thin brown layer can be a solid coating on a wall or a baffle between two fluids. In the immediate wall vicinity, temperature variation is linear within each material, as shown in this plot. The heat flux is the same at the interface between fluid and coating, and between coating and solid on the other side, or fluid if it is a baffle rather than coating. However, because the conductivity is different in each material, the slope in temperature variation is also different. The heat flux on fluid side is equal to the product of conductivity and temperature gradient in fluid. If conductivity in fluid is temperature dependent, which usually is the case, it should be determined for the temperature at the interface Kf. Within coating or baffle, the same heat flux is determined as the product of conductivity and temperature gradient, which can be expressed as this temperature difference divided by the thickness of the layer. The same flux passes through the material on the other side of the layer and is expressed as the conductivity of that material times temperature gradient. Assuming that the grid resolves the laminar sublayer near wall, that is, y plus is around 1, discrete approximation of gradients by linear profiles leads to the following expression for the heat flux at wall. The temperature gradient on fluid side is expressed as the temperature difference between wall and auxiliary node C' divided by distance, which is defined by this expression. Analogous approximation is used on the other side of the coating layer. If we introduce local resistances alpha as the ratio of conductivity to distance and perform some rearrangements, we arrive at the following expression for heat flux as a function of temperatures at auxiliary nodes T and K' and Tc'. This provides a direct link between temperature fields on both sides of the interface and allows an efficient simultaneous solution of the energy equation in all continua. If we introduce an effective resistance coefficient and effective conductivity, the expression for the heat flux can be rewritten as shown in these two expressions. The temperature at auxiliary nodes C' and Nk' must be obtained by interpolation from surrounding cell center values. One possibility is to use the variable value at cell center and the gradient at cell center, which is a second order approximation corresponding to linear interpolation, as given by these expressions. The coordinates of auxiliary nodes are determined by these relations. Distances delta f and delta s are defined on preceding slide. In general, heat flux is computed using temperatures and gradients at cell centers on either side of interface as follows. The first term on the right-hand side contributes to the coefficient matrix and links implicitly the solutions in fluid and solid. The underlying term is treated using the deferred correction approach. The underlying part is zero when the grid is conformal and orthogonal at the interface. It is hence desirable to pay attention to this feature when generating the grid. In external flows, heat transfer from a wall to its environment with temperature T infinity is expressed via the heat transfer coefficient alpha and temperature difference between wall and environment. Many users of CFD codes want to compute and visualize the heat transfer coefficient at walls in internal flows, for example on turbine blades or hot engine surfaces. This is tricky because the heat transfer coefficient must always be defined together with the reference temperature. They must come as a pair. There is no obvious choice for the reference temperature in internal flows. Commercial CFD codes offer various options, for example, temperature at a location with a prescribed Y+. Heat flux, that is, heat transferred per unit area, is the quantity that converges toward grid-independent solution as the grid is refined, and it is the best quantity to visualize. This plot shows temperature distribution from computing heat conduction in a rectangular 2D body with isothermal side walls and adiabatic top and bottom wall. The temperature distribution is linear, and the same result would be obtained for any material. What differs depending on material is the heat flux through isothermal walls. It is higher for materials with a higher thermal conductivity. Because the temperature varies linearly between isothermal walls, the temperature gradient at both walls can be expressed as the temperature difference divided by distance, leading to this simple expression for the heat flux. The heat flux per unit area given by this expression is constant along isothermal walls. For a non-rectangular geometry, the picture changes, as can be seen in this plot of temperature distribution. The isotherms are denser near these two corners and are further apart near these two corners. There is no simple formula for heat flux calculation in non-trivial geometries. One must perform numerical computation of heat conduction to obtain the heat flux at isothermal walls. The heat flux at walls is non-uniform. It is higher where isotherms are denser. Isotherms must be orthogonal to an adiabatic boundary. Adiabatic means zero heat flux, and zero heat flux requires zero derivative of temperature in the direction normal to boundary. One should always check that the numerical solution satisfies this condition, which is here obviously the case. For a composite body, the situation again changes. Temperature variation within each material is different depending on its conductivity. The same amount of heat is carried across each slab because top and bottom walls are adiabatic. Where conductivity is lowest, in steel, temperature gradient is the highest and vice versa. In the material with the highest conductivity, copper, isotherms are almost vertical because heat is transferred only in x direction. This plot shows temperature variation along the horizontal line at half height. Temperature varies linearly within each slab, and because the heat flux is the same through each material, the slopes are inversely proportional to the material conductivity, lowest in copper and highest in steel. How much heat is needed to raise the temperature of a body to a certain level can easily be determined, knowing its mass and the specific heat capacity. However, how long this takes under particular conditions is not so easy to determine. The transient process of heating up a body that is initially cold is often of interest in engineering, as well as cooling down a hot body. Finding how long it takes is often important. This plot shows the variation of heat flux through the hot wall, red line, and the cold wall, blue line, during heating up of a steel block with initial temperature equal to cold wall temperature set to 300 K, when the hot wall temperature is suddenly raised to 310 Kelvin. The heat flux at the hot wall is initially very high because of a very high temperature gradient. For a while, heat flux at the cold wall is zero because the temperature gradient is zero. Initially, the whole block has the cold wall temperature. As the material near hot wall gets heated up, the heat flux reduces, and when the temperature of the material near cold wall starts increasing, the heat flux through the cold wall also starts increasing. It takes about 1500 seconds until the steady state with a linear temperature distribution and equal heat fluxes at both isothermal walls are obtained. This plot shows temperature distribution at an early stage, while this plot shows the steady state. If the body was made of aluminum instead of steel, the heating up process would take circa 50 seconds to reach the steady state, 30 times faster than with steel. With fluids, we cannot perform an experiment with conduction heat transfer alone because we cannot stop fluid from moving, and as soon as the fluid is in motion, convection is involved. However, in simulation, we can solve only the energy equation in a fluid domain, like in solid. Let us look at a 2D cavity filled with air, whose length is 25 mm and height 22.5 mm, with hot wall temperature Th equals 310 Kelvin and cold wall temperature Tc equals 300 Kelvin. In the case of conduction alone, the temperature varies linearly between hot and cold wall, as shown in this plot. When we solve both the Navier-Stokes equations and the energy equation, temperature variation causes density variation, and this sets fluid in motion, as shown in this plot. Air rises up along hot wall and falls down along cold wall because density of gases reduces as the temperature increases. The flow leads to a different temperature distribution compared to the case with conduction alone, as shown in this plot. This plot shows temperature profiles along horizontal line for conduction alone, the blue line, and for conduction plus convection, the red line. In the natural convection case, the temperature gradient near isothermal walls is much higher than in the case of conduction alone, which leads to a significantly higher heat flux. The ratio of heat fluxes with and without convection is called Nusselt number, and in this case it amounts to 2.45. Natural convection flows are characterized by Rayleigh number, Grashof number, and Prandtl number, which is a fluid property. The Rayleigh number given by this expression is equal to the product of Grashof number and Prandtl number. In this particular case, Rayleigh number is equal to 1.053 times 10 to 4. By doubling the cavity size for the same fluid and temperature difference, the Rayleigh number increases by a factor of 8. Temperature distributions and Nusselt numbers change substantially with increasing Rayleigh number. These three plots show temperature distribution, flow pattern, and temperature profile along horizontal center line when the cavity size from preceding slide is doubled. In these plots, the cavity size was doubled one more time. With increasing cavity size, temperature gradient at isothermal walls increases and isotherms tend to be horizontal in central part of the cavity while they become denser near isothermal walls. The Nusselt number roughly doubles when the cavity size is doubled. Increasing the cavity size further leads eventually to a turbulent flow. Boundary layers at isothermal walls become thinner and the Nusselt number increases further, almost doubling when the cavity size is doubled. The fluid is stably stratified and almost stagnant in most of the cavity volume, with high velocities only along isothermal walls. Here, Run's equations were solved with the default K-epsilon turbulence model in Simpson-Testaces M+ software. The same configuration was also analyzed in a three-dimensional cavity using large eddy simulation approach and the Smogorinsky subgrid scale model. The cavity size is the same as in the last example from the preceding slide, but with a twice higher temperature difference of 20 Kelvin, thus doubling the Rayleigh number to 8.6 times 10 to 7. These two plots show instantaneous flow field and temperature contours. The results are similar to those presented in the preceding slide for a 2D flow domain, only the boundary layers on vertical walls are thinner because of a doubled Rayleigh number. Large eddy simulation started with fluid at rest. It takes over 100 seconds until the flow develops to a quasi-steady state, as can be seen from this plot showing the heat transfer through the isothermal walls. It will still take some time until the heat transferred through the two isothermal walls becomes on average identical. Temperature is nearly constant and vertical velocity component nearly zero in the middle part of the cavity, as can be seen from instantaneous profiles at mid-height in symmetry plane shown in these two plots. A polyhedral grid with 12 prism layers along walls was used. A part of the grid in one section plane near a corner is shown in this plot. In addition to cavity height, fluid properties also affect Rayleigh number and thus the flow pattern. These three plots show temperature contours, flow pattern, and temperature profile along horizontal center line from a 2D simulation of natural convection in a cavity 50 mm wide and 45 mm high and filled with air, with left wall being hot at 310 Kelvin and the right wall being cold at 300 Kelvin, and the other two walls being adiabatic. The Prandtl number for air is 0.712, which leads to the Rayleigh number of 8.4 times 10 to 4. The Nusselt number for the resulting flow came out as 4.67. These three plots below are for the same cavity and the same boundary conditions, but filled with water. The Prandtl number for water is 5.16 and the resulting Rayleigh number is 2.03 times 10 to 7, which is much higher than the Rayleigh number when the cavity is filled with air. While the flow in air was laminar, in water it is turbulent, and the Nusselt number is much higher, 24.6. For most fluids, density monotonically decreases as the temperature increases. Boussinesq-approximation described in slide 5 assumes linear variation of density with temperature and can be used if temperature differences are small. Water is an exception. Its density is maximal at approximately 277 Kelvin or 4 degrees Celsius, as can be seen from these two plots showing the initial linear temperature distribution across cavity and the corresponding density variation. In this nonlinear range of density variation with temperature, Boussinesq approximation cannot be used. These two plots show temperature distribution and velocity vectors in a 2D cavity whose length was 25 mm and height 22.5 mm. The hot temperature on the right was Th equal 281.15 Kelvin or 8 degrees Celsius, and the cold wall temperature on the left was 0 degrees Celsius. The top and bottom walls were adiabatic. Water is rising up along both hot and cold wall and falling down in the middle where the density is the highest. When bottom wall is hot and top wall is cold and side walls are adiabatic, we have unstable stratification with complicated 3D flow patterns. Blobs of hot fluid rise up while blobs of cold fluid fall down. Run's approach is not suitable for this kind of flow. Large eddy simulation works best. These videos show animation of flow pattern and temperature variation in one vertical center plane from a large eddy simulation of natural convection flow in a cavity filled with air which is 0.4 meters tall with a base size of 0.4 times 0.32 meters, hot bottom wall at 305 Kelvin and cold top wall at 295 Kelvin. We see in these animations occasional ejections of hot blobs of fluid from the vicinity of bottom wall as well as cold blobs falling down off the ceiling. This plot shows instantaneous wall shear stress on bottom wall, highlighting the complex flow pattern in the vicinity of hot wall. This plot shows the variation of heat transfer with time at the two isothermal walls. On average, the same amount of heat is transferred at both walls, but temporarily heat is both accumulated in and drained from the cavity. When the cavity height is small relative to length and width and bottom wall is hot, convection cells form, called Bénard cells. They can be stable, as can be recognized from this plot of wall shear stress pattern on top cold wall in a cavity with dimensions L equal B equal 50 mm and height 2 mm, and with bottom and top wall temperatures Th equal 325 Kelvin and Tc equal 305 Kelvin. The fluid is water and the computational grid is Cartesian with 200 by 200 by 32 cells. The cell size is 0.25 by 0.25 by 0.0625 mm. This plot shows the heat transfer through the bottom hot wall, which quickly becomes constant. The flow is steady and laminar. These two plots show flow pattern and temperature distribution in one vertical section plane. Where the plane cuts across convection cells, we can see how water circulates with hot blobs rising up and cold blobs falling down. Let's have a brief look at a natural convection flow in a more complex geometry. A hot cylinder with a diameter d equal 40 mm and temperature Th equal 400 Kelvin is placed in an enclosure with cold top and bottom walls at Tc equal 300 Kelvin and adiabatic side walls. This plot shows instantaneous temperature distribution in one vertical section plane from LES simulation using Smagorinsky subgrid scale model. Below the cylinder, we have stable stratification with a hot cylinder above cold wall. This is why the flow is very weak in this region. Above the cylinder, we have unstable stratification with a hot cylinder below top cold wall. We see a plume of hot fluid rising up above the cylinder toward the top wall. The animation shows the variation of velocity field in the same section plane. The hot plume rising from the cylinder is unstable. When it hits the top wall, it displaces the cold fluid which moves along the top wall toward side walls, where it then falls down, but not far below the cylinder. These two plots show the normalized heat transfer through the cylinder wall and the two cold walls, computed using LES and Run's approach. The difference between Nusselt numbers from the two simulations is very large, more than 15% relative to the value from LES, which is considered more accurate. This shows that unsteady run simulation is not suitable for flows with large-scale motions, which are neither statistically steady nor periodic. Here is an example of a laminar forced convection flow of a cold fluid at the temperature Tc equals 300 Kelvin around a hot cylinder at the temperature of Th equals 500 Kelvin in a channel at Reynolds number equal 200. Vortex shedding behind cylinder takes place, as is visible from these plots of instantaneous velocity field and instantaneous temperature. Heat flux at cylinder wall is highly non-uniform. It is highest on the front side of cylinder, where cold fluid comes in contact with a hot cylinder surface, and lowest around separation points, where low velocity heated up fluid stays longer in contact with cylinder wall. In this and many other forced convection flows, temperature variation has a minor effect on the flow field, contrary to natural convection flows, where temperature variation is the sole cause of fluid flow. Let's have a look at another example of a forced convection flow. A hot 90-degree elbow at the temperature Th equals 500 K is connected to straight pipes with adiabatic walls. At inlet, a cold fluid at the temperature Tc equals 300 Kelvin enters the pipe with a velocity corresponding to the Reynolds number of 200,000. Only half of the flow domain is considered, assuming symmetry conditions. These two plots show pressure and Y+ contours on elbow and pipe surfaces. The adiabatic straight pipe segments are much longer than shown here. Computations were performed on 3 trimmed Cartesian grids with prism layers on walls. Cross sections through all 3 grids are shown in these plots. The thickness of the first prism layer at the wall was 0.3 mm, corresponding to Y+ between 21 and 44 in all 3 grids. The thickness of all prism layers was 3 mm on grid 1 and 2.5 mm on grid 2 and grid 3. The number of prism layers was 5 on grid 1, 6 on grid 2 and 8 on grid 3. Outside prism layer, grid spacing was halved with each refinement. Computations were performed with Simpson-Testacic software using the RANS method and the K-epsilon turbulence model with wall functions. This figure shows residual histories on all grids. Computation on the next finer grid was started with an interpolated solution from the next coarser grid. As the fluid flows into the bend, the pressure is increased at the outer wall and reduced at the inner wall, as can be seen from pressure plot on the wall. See preceding slide for a detailed view. This leads to a pressure-driven secondary flow, as shown in the vector plot in the cross-section at the exit from the bend. Shown are projections of velocity vectors onto the section plane. Along wall, vectors are directed from the zone with high pressure toward the zone with low pressure. The low momentum fluid near wall must flow in the direction of reducing pressure. In symmetry plane, the fluid has more momentum and thus can flow against the pressure gradient, but it is slowing down along the way. Forces on bend, heat transfer through bend wall, and pressure drop from inlet to outlet were monitored and compared for all grids in this table. The difference between solutions is surprisingly small. The heat transfer through the hot bend wall differs between solutions on grids 2 and 3 by only 0.16%. The last example is the simulation of heat transfer in a model of a heat exchanger involving 2 fluid streams and a separating wall between them. Simultaneous heat transfer through solid and fluid is called conjugate heat transfer. These plots show the computational grid in one longitudinal and one cross-section through the solution domain. Simpson-Testacic software creates in such a geometry a conformal interface between grids in fluid and solid region. In addition, the grid in the thin solid region is prismatic. The polygons from wall surface on one side are projected onto the interface on the other side. This simplifies the computation of heat fluxes at interfaces, as discussed in slide 10, and increases both the accuracy of solution and the efficiency of the solution method. The rectangular channel has dimensions 30 by 30 mm and its walls are diabatic. The pipe inner diameter is 20 mm and the pipe wall thickness is 1 mm. The wall material is steel, while the fluid on both sides is water, flowing at 20 meters per second in both streams, but in opposite directions. Computations were performed with Simpson test RCCM plus software using the RANS method and the K-epsilon turbulence model with wall functions. 4 grids were used in a grid-dependent study. Grids have 6 to 8 prism layers with a stretching factor from 1.15 to 1.3. The total prism layer thickness is 1 mm and the first layer next to wall is 72.8 micrometers thick on all grids. This results in the average Y plus on pipe wall around 30, which is acceptable when wall functions are used. Heat transfer from hot to cold fluid is monitored on both sides of pipe wall. At convergence, the values are identical at 6 or more significant digits. This plot shows the computed temperature profile across pipe wall at midsection. Note linear temperature variation across pipe wall and very high gradients in fluid next to wall on both sides. Because the heat exchanger model is very short, the effect of heat transfer has not propagated far into the streams yet. The table shows the variation of heat transfer with grid refinement. It is not monotone, with results from grids 2 and 3 being almost identical. The difference between values obtained from grids 3 and 4 is only 0.07%. Here is a summary of this lecture. Heat is transferred between fluid and solid walls by conduction. Heat flux is proportional to conductivity and temperature gradient at the interface and is the same on both sides. Fluid flow and turbulence enhance heat transfer by increasing the temperature gradient at walls. Simulation of heat transfer requires therefore an accurate prediction of fluid flow, especially in the near wall zone. Prism layers are important. Care is needed to account for variable fluid properties and all relevant boundary conditions, which often requires solving the energy equation also in solids surrounding the flow domain, that is, a simulation of conjugate heat transfer. RAS approach is suitable for statistically steady or periodic flows. Unsteady flows, as in the case of unstable stratification, require a transient solution. LES approaches are usually more appropriate.